In this lesson, we're going to review some operations with radicals. So first, we need to recall how to simplify square roots. So for this example, we're going to be simplifying completely, and we want to assume the variables represent non-negative real numbers. So first, we want to simplify the square root of 128. If I tried to do the square root of 128 in my calculator, I would get a decimal. So what that means is that it is not a perfect square. So I need to simplify it. So when we simplify, we always try to find the largest perfect square factor of 128. Now, sometimes there are multiple perfect square factors of the number, which is true for this case. We actually have a few different perfect squares that will end up working, but we want the largest one. If you need help to find the largest one, my suggestion is to make a list of all your perfect squares. 1 squared is 1. We don't really need 1 to help us with simplifying, but starting at 2, so 2 squared is 4, 3 squared is 9, and list out all of them, so 4, 9, 16, 25, 36, and so on. Then figure out where the number you're trying to simplify lies. So for example, 128 falls between the perfect squares of 121 and 144. And then just work backwards and say, okay, well, starting at the largest perfect square that's smaller than 128, is 121 a factor of 128? Well, if you're not sure, plug it into your calculator. 128 divided by 121. If you get a whole number, wonderful, it works. If not, then you keep going down the line. So 121 is not a factor of 128. Keep going backwards. 100 is not a factor of 128. 81 is not a factor of 128. But 64 is a factor. 64 times 2 will give you that 128. Like I said, in this case, we actually have more perfect square factors. 16 times 8 would have worked, and 4 times 32 also would give you 128, but we want the largest perfect square factor. Once we find the largest perfect square factor, we want what its factor pair is. So 64 times 2, we need both of those numbers. And what we do is we're going to be taking the square root of each of them. So I like to think of our first square root is our perfect square root. So I'm going to put the 64 in our first square root. And then the second one is our extra number, our non-perfect square. So it's better to put this perfect square first, because then we want to actually figure out what that is. So the square root of 64 times the square root of 2, again, square root of 64 is a perfect square, so we can take the square root of 64, which is just 8, and then the square root of 2 will just stay. So the square root of 128 is just equal to 8 square root of 2. Again, if you did not find the largest perfect square, if you chose 4 and 32 or 16 and 8, just like we're reducing a fraction, if it can be reduced more, you would need to reduce it completely. Here with simplifying a radical, if you can simplify more, you would have to. So if you chose 4, you would get 4 and 32. Well, 4 is your perfect square. That would go in the first square root. The 32 would go in the second square root. But then 32, I can simplify again. And then you just keep simplifying it until you have something inside the radical that does not have a perfect square factor. So continuing on to part B, we have a few things going on because we have the square root of 162 x squared y to the 5th. So since we haven't talked about exponents yet in variables, I'm going to work through this in a few different pieces. First, just based off of what we just did, I want to figure out what the square root of 162 is. So following the steps that we just took, again, you can go back up and look at your perfect square list and say, okay, what's my largest perfect square that goes into 162? And that's 81. So I can break down 162 into the square root of 81 and the square root of 2, because then the square root of 81 is just 9. So square root of 162, if that was the only part we would have, would give you 9 square root of 2. Another quick comment is that when we take the square root of the number, the square root of 81 is just 9. It stays 9. We don't try to take the square root anymore. Square root of 81 is 9. So next I want to look at my exponents. I'm going to work through this in two separate steps as well. The next part is that I need to do the square root of x squared. Well, this, if you look in your textbook, is actually a formal definition. The square root of x squared is actually equal to the absolute value of x. And the reason for that, I'm going to kind of come up to the top real fast and show you why, is that if I had, for example, the square root of, let's say, -3 squared, and I also had the square root of 3 squared. Well, -3 squared is 9, so I'd be doing the square root of 9, and then 3 squared is also 9. So the square root of 9 and the square root of 9 are both going to give us 3. So what we're saying here is that inside, that x represents the -3 in the 3 that in the problem that I just did, is that inside I could either have a -3 and square it and get an answer of +3, or I could have a +3 and square it and get that same answer of +3. So when we're taking the square root of x squared, this actually comes out as an absolute value of x, saying that the inside could either be a positive or a negative number, like we have with the positive or -3. With this problem and with most of the examples that you're going to end up seeing, the problems you're going to work through, the directions are really important because it says assume the variables represent non-negative real numbers. So we can actually say that this is equal to just x, the absolute value of x is equal to x, since x has to be greater than or equal to 0 because of the directions. Okay, so the square root of x squared technically becomes the absolute value of x, but our direction said that we want non-negative real numbers, so that means that we would just make the absolute value of x equal to x. This is only an issue if you have the square root of x squared, square root of y squared. Any other square root that we're going to be taking won't be as much of an issue. Finally, then, we get into the square root of y to the 5th. So here, the square root of y to the 5th, it looks like I can't do it. What we do is we try to take the square root by dividing the root into the exponent. So although it's not written, there is an implied 2 out here in our radical. And what we're doing is we're trying to divide 2 into 5. Well, 2 can't go into 5 evenly. But if I think back to my handy-dandy long division, you can do this in your head. You don't have to work it out like I am. I'm doing 2 goes into my exponent of 5. Well, 2 goes into 5 2 times. And then if I work through this, 2 times 2 is 4. We would have a remainder of 1. Well, how that helps us is that the quotient that we got in our long division, this 2, is saying how many times the root goes into your exponent. Well, since it goes in 2 times evenly, I can rewrite the square root of y to the 5th as y to the 2nd. That power of 2 came from the quotient that I just found. And then my leftover is the remainder, saying that I can have the square root of y to the 1st, or just y squared, square root of y. Again, where this comes from is another way to work through this, whichever you prefer, is that the square root of y to the 5th, I can rewrite this as the square root of y to the 4th times the square root of y, because remember, all I'm doing is I'm kind of working backwards from that product rule that you had earlier with exponents, that y to the 4th times y to the 1st, 4 plus 1 would be 5. So I can break this down, because then using that same idea as doing your root into the exponent is that we have a 2 out here. 2 goes into 4 2 times, or 4 divided by 2 is 2. So I can simplify this into y squared square root of y. It's up to you how you want to think of it. The second way that I showed you shows how we break it down, similar to using that idea of finding the largest perfect square factor. The largest perfect square factor of y to the 5th would be y to the 4th. Or if you'd rather just think and not have to show as much work, really, is that we're just doing back for the original way that I showed it. 2 goes into 5 2 times. That comes out as your power on the outside. And then you have a remainder of 1. So that's your power on the inside. So we have y squared and then square root of y. Finally, we need to put all these pieces together. So I purposely separated it so you can see each of the moving parts. Anything that's not under the radical would be on the outside. So I have the 9 on the outside, the x, and then the y squared. and then anything underneath is going to stay underneath. So in my first piece, I had a 2, square root of 2. My second piece, I did not have anything underneath this radical, and then I had a y. So your final answer then is 9xy squared, square root of 2y. So here we're just going to work through 2 problems with multiplication in order to show how to multiply radicals. So what we do want to do is we want to multiply under the radical first. We are allowed to multiply under the radical. So here we would just multiply our like pieces. So we would do 5 times 15 to get 75. And then we would do x times x to get x squared. Now from here we want to simplify. So essentially when you're multiplying radicals, you want to multiply, then simplify. So we're left with the square root of 75 x squared. So simplifying this part then, I want the largest perfect square factor of 75, which would be 25. And then 25 times 3 would get us to 75. X squared, I am going to be able to take the square root of. We just saw that in example 1. So I'm going to put x squared in that perfect square radical to show that I'm going to be able to take the square root of it. So the square root of 25 is 5. Then the square root of x squared we just saw is the absolute value of x. Square root of 3 will just stay square root of 3. Going back to my directions, we're assuming that the variables represent non-negative real numbers. So we can say that the absolute value of x equals x, since by the directions it's saying that x is greater than or equal to 0. So I can rewrite this then as 5x square root of 3. Same idea on the bottom one, but now we have a cube root. Still the same process as long as I'm multiplying a cube root and a cube root here. I'm going to have the cube root of 4 times 4 is 16. X squared times x is going to be x to the third. Then I want to simplify this. So we want to simplify this in a similar way that we simplified square roots. With cube roots though, we want to find our largest perfect cube factor. So your perfect cubes would be 1 to the third is 1, 2 to the third is going to be 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, and so on. So we want our largest perfect cube factor of 16. Well, we don't have to go very far because 8 would end up being the only perfect cube factor other than 1. So looking at what we have then here is that I'd break this down into 16 is going to be 8, and then in another cube root we would have the 2 to show the 8 times 2. Then we have the cube root of x to the third, which I can do that. Because remember, you're dividing your root into your exponent. So 3 goes into 3 one time. So I'm going to put the x to the third with that cube root of 8 to show that I'm taking the cube root of that number. So here we have the cube root of 8 is going to be 2. The cube root of x to the third, again, 3 goes into 3 one time, so I have an x to the first, or just x, and then that leftover cube root of 2 will just stay. So note here, I did not need to have that absolute value because anything to the third power, if it's positive, would be positive. If it's negative, it's going to be negative because you're multiplying it an odd number of times. So I don't need that absolute value only when we're doing the square root of x squared, square root of y squared. Any other root for right now is not going to be necessary. So now we just want to do an example with dividing with radicals. So when we have just one radical, as we can see for both of these examples, we first want to try to see if we can simplify within the radical first. If we can, wonderful. If we can't, then we're going to need to take the root of the numerator and the denominator. So for part A, we have the square root of 121 over 64. 121 over 64, I can't reduce that at all. There's no other simplification that I can do, which means that I would just start by taking the square root of your numerator, 121, over the square root of the denominator, 64. And then we would just do that work. So since they're both perfect squares, it makes our life a lot easier. The square root of 121 is just 11. The square root of 64 is 8. And we are done. For part B, looking at what we have inside the radical, it looks like we can simplify this. Remember, when we are simplifying, we still have the square root around it. So 60 divided by 3 would just be 20. x to the 5th divided by x, well, remember that's a power of 1 in the denominator, so x to the 5th divided by x to the 1st, subtract your exponents when you're dividing, you're left with x to the 4th. From here now, since we still have that square root, we do want to simplify. So 20, our largest perfect square factor of 20 is 4. And then 4 times 5 would get us to 20. So just for 20, I have the square root of 4 times the square root of 5. But then that x to the 4th, we need to determine where that's going to go. Well, again, remember we have that little 2 hanging out here. And we would say, can 2 go into 4 evenly? It can, so that way we are just left with an x squared after we take the square root of it. So for right now, I'm going to put the x to the 4th in the perfect square radical with the 4 to illustrate that we are going to be able to take the square root. So finishing this out then, the square root of 4 is 2. As I just walked through, the square root of x to the 4th, 2 goes into 4 2 times, so we have an x squared. And then we're left with the square root of 5. Finally, we just want to walk through an example of adding and subtracting radicals. So the steps are the same no matter if you're adding or subtracting. Your first step here is that you need to simplify the radical first. Think of adding and subtracting radicals as combining like terms. We cannot add or subtract under a radical. We need to have like radicals in order to add or subtract, which means we need to simplify first. So our 4 square root of 12, that 4 is just going to hang out on the outside until I simplify the square root of 12. So I'm going to have 4, and then square root of 12, largest perfect square factor is going to be 4, and then we're left with a square root of 3. I'm going to keep simplifying this down until I'm completely simplified, and then I'm going to go over to the 2 square root of 75. So 4, square root of 4 is just 2. And then square root of 3. So now what happens here is that we have this 4, and what this really means is that we have 4 times 2 square root of 3, and we want to do that multiplication. So although we haven't seen the 4 on the outside or a number on the outside before, whenever that happens, it's going to be multiplied by whatever number came out of our square root. So 4 times 2 is 8 square root of 3. So 4 square root of 12 simplifies to 8 square root of 3. I'm going to repeat that process for the 2 square root of 75, so I have a subtraction throughout all of these. So square root of 75 would break down to square root of 25 and the square root of 3, because 25 is the largest perfect square factor. Then square root of 25 is just 5, which means that we then have 2 times 5, which would be 10, and we still have that square root of 3. At this point, our next step would be to combine like radicals. So what I mean by like radicals is that we need to have the same number under the radical. So the fact that we have a square root of 3 and a square root of 3 is very good for us, because just like when we're combining like terms with x's, if I had 8x minus 10x, we would add or subtract the coefficients. So here I would do 8 minus 10 to get a negative 2, and the x would stay. It's that same idea here with radicals, is that I'm just adding or subtracting the coefficients. So that way we have that 8 minus 10 is going to be negative 2, and we just keep that square root of 3, which is our final answer then.